All right, so the first speaker of the afternoon session is Bidyut Sanki, who will talk about isoperimetric inequality for disconnected regions.
Thank you. I'd like to thank the organizers for inviting me. So this is the title. This is joint work with ARIA, and this is appeared in Geometry Dedicata 2025. So let us begin with the following basics. So this talk is going to be very basic talk. So plan. So we begin with discrete isoperimetric inequality. Then the question, we ask the question on isoperimetric inequality for disconnected regions. Inequality for disconnected regions, then motivation, finally main results. Okay, so let us begin with the following question. So discrete isoperimetric inequality asks that among the set of all n-sided polygons with a given fixed area, which one has the least perimeter? So this is the question. It has an equivalent dual problem. So basically among this asks that among the set of all n-sided polygons with a fixed perimeter, which one has the largest area? Okay, so and answer is the regular one. That is, the side lengths are equal and interior angles are equal. So let us polygons more precisely in, let's say M, and M is equal to Euclidean plane or sphere or the hyperbolic plane. And for reference, for M equal to R2, so this is basically very easy, and so easy exercise. So still reference can be found in regular figures by LF dot. So for Euclidean case, you can find the proof in page number 160, and for m equal to sphere, the same reference, page number 213 to 214. And for m equal to hyperbolic plane, Karoli Bejdek 84. So basically, Bejdek, he has given a proof on R2 and stated that the same strategy will work for spherical and hyperbolic geometry also. And recently, and Gupta, so Vasudev Datta and Subhojoy Gupta, they have proved the following theorem. So the article name is Isoperimetric inequality for non-Euclidean geometry for non-Euclidean polygons. So the statement is following: among all hyperbolic, respectively spherical, among all hyperbolic n-gons with a fixed perimeter, the regular one has the largest area. So this is basically the dual state proof of the theorem for which answers the dual question. Okay, and so here for isoperimetric inequality for disconnected regions, we ask the following question. Suppose, so basically what we do is we split the area into parts, like, so let us define. So let P be a regular n-gon, or where n is greater than or equal to 3, of course, in M. So M is either Euclidean plane, sphere, or the hyperbolic plane, and we define a configuration of polygons by, so C is equal to P1, P2, and so on, Pk. So this is a finite set of polygons. Called a configuration of polygons. And we define area of this configuration. See, this is equal to summation of areas of the polygons in the configuration. So summation over I equal to 1 to k, and this is called the total area of the configuration. And perimeter of the configuration C, this is equal to summation perimeter of Pi, summation over I equal to 1 to k. So this is called total perimeter. of the configuration C. So now we suppose that area of the configuration of configuration C, this is equal to, that is the total area of this configuration of polygons. This is equal to the area of P, and the number of sides of each polygon in the configuration C is less or equal to, let's say, n. So where P is the polygon, number of sides n. Now we are looking for, so when does the inequality so what we expect, perimeter of the polygon P, this is less than or equal to perimeter of the configuration C, that is perimeter Pi, summation over I equal to 1 to k. So this hold. So this is the question we will study here. So its motivation. So let SG, so SG denotes the closed and oriented topological surface of genus G. Yeah, for all I equal to 1 and so on up to k. So SG closed and oriented topological surface of genus G. Closed means compact without boundary, and so we define filling so a set of simple closed curves, gamma 1, gamma 2, and so on up to, so gamma, let's say m of simple closed curves on the surface SG is called a filling if these curves are in minimal position. So in the intersection number I of any two of them, gamma I, gamma j, this is nothing but the number of points in their intersection, gamma I intersection gamma j. So that is they are in minimal position pairwise, and second condition is the complement of their union is G minus union gamma I over I equal to 1 to m. So this is disjoint union of topological disk. So D, let's say D j equal to 1 to some b, where b is some natural number, and D j, this is topological disk for every j. Okay, so this is the definition of filling of a surface. And so to a filling, one can associate two natural numbers. So number of curves, that is m, that is called size of the filling, and number of disks in the complement b. So if m equal to 2, then we say that omega. This is a filling pair. And B is at least 1. Okay, so B is greater than or equal to 1. So when B is equal to 1, then we say that the filling is minimally intersecting. In such a situation, number of intersection points of the curves gamma I will be minimal. So for B equal to 1 and M equal to 2, gamma is called minimally intersecting filling pair. Minimally B is number of complementary disks. So it is given here. So union of disks. Yeah. So okay. So example. So one can construct filling pair. So generating filling pairs. So you consider one. So suppose you are given any closed and oriented surface SG. So this is S2. So G equal to or SG, G equal to, here it is in particular, it is 2. Now you consider a pair of bands decomposition, gamma 1, gamma 2 to gamma 3G minus 3. Now we consider a simple closed curve. Let's say this is, let's say, alpha. Now, so T gamma 1 or T gamma, this is den twist about the curve gamma. So now consider beta is equal to the product of den twist along the bands curves T gamma 2, T gamma 3G minus 3 acting on alpha. Okay, so then the pair alpha comma beta, this gives a filling pair, is a filling pair on SG. Okay. So here you will get filling pair where you have 4 complementary disks. Okay. So this is a construction of filling pairs, and so OGAV 1. So in 2015, so in their article, so the title is minimally intersecting filling pairs. On surfaces AGT. So they have studied minimally intersecting filling pairs in this article, and so basically what they have done, they corresponding to minimally intersecting filling pair. So they have defined a permutation, okay, that associates with the minimally intersecting filling pair, and that is called filling permutation, okay. That has some properties, and corresponding to filling permutation, you can have, conversely, you have for to a filling filling permutation, you will have a minimally intersecting filling pair. And also they have counted the mapping class group orbits of minimally intersecting filling pairs. Furthermore, they have defined filling pair length function. So let sigma g, this is the set of all filling pairs on SG, and also we define for k greater than or equal to 1, of course. So sigma kg, so this is equal to alpha comma beta in sigma g such that SG minus alpha union beta, this is union of disjoint union of topological disk dj, j equal to 1 to b, where b is less or equal to k. So at most k many union of k many disjoint union of topological disk. So this is sigma g k, and so now mg, this is Teichmüller space quotient with the mapping class group of genus G, and this is called the moduli space of hyperbolic surfaces of genus G. So this is basically the set of all hyperbolic surfaces of genus G. So no, that is not minimally intersecting. On torus it is trivial, so just consider meridian. On genus 2, there is no minimally intersecting filling pair. So genus G greater than or equal to 3, you have. Right, yeah, right now I think I can draw some example. I can give you some example. Okay, so for x belongs to the moduli space of genus G, Mg, and alpha comma beta, a filling pair on SG. So basically, yeah, so these are simple closed curves, okay, and on hyperbolic surface. So if you have a simple closed curve, so in its free homotopy class, you have a unique geodesic representative. Okay, so we consider alpha and beta, they are geodesics, okay, simple closed geodesics in X, and they fill the surface X. So alpha beta simple closed geodesics in X. So consider, we define L x of alpha beta, this is equal to the length of alpha in X plus length of beta in X. So this sum of length of alpha and beta. So this is called filling pair length function. then we have a function. So the definition of the one. So if G superscripted with K, so this is a function on moduli space of genus G to set of all reals defined by f G K of alpha, okay, so of X. So X belongs to Mg. So this is equal to L alpha comma beta in the surface, so X over alpha comma beta belongs to sigma G K, okay, and take its infimum. So you can take minimum also. So its infimum attains at some point. Okay, so this is the function they have defined, and so this function is has many important properties, like this is topologically morphed function, it is proper, and they have studied its bound, okay, and you know this function is unbounded above, and the theorem. So they have shown that fg k of x, so this is greater than or equal to mg over 2 for the values k equal to 1 and 2, where mg is nothing but the perimeter of a right angle 8g minus regular foregone in the hyperbolic plane, where mg, so this is equal to 8g minus 4 times cos inverse 2 times cos pi over 4g minus 2 plus 1. So this is basically a side length of a right angle 8g minus regular polygon. And yeah, and yeah, so G comma B equal to 2 comma 1, this is not allowed. So we consider G comma, yeah. So G comma B is not equal to 2 comma 1. Okay. Then they have defined another function yg from mg to r. So here replace sigma gk by sigma g only. This is a general function. So yg of x, so this is equal to infimum of L, so L x alpha beta, such that alpha comma beta belongs to sigma g, and this is called filling pair systole function, called filling pair systole function. So this is basically a generalized systole function, And so this function is also Morse. And they conjectured that the same bound, so again, this function is unbounded above. So this function is unbounded above. This is also proper function in topological Morse. And they conjectured that YG is bounded below by mg over 2. So YG of x, this is greater than or equal to, this is greater than or equal to mg over 2. So, and this conjecture is obtained by following. Idea. So consider x belongs to mg and alpha comma beta belongs to sigma g. Again, we consider alpha and beta. They are simple closed geodesics. We cut the surface x, cut x along alpha union beta. So the result is a configuration of polygons. Okay, so P1 and so on up to P B. So configuration of hyperbolic polygons. So one immediate observation is sum of the areas of these polygons is a total, that is total area of Pi summation over I equal to 1 to B. So this is equal to area of the surface x, and this is equal to minus 2 pi Euler characteristic of the surface x, or Sg, and this is equal to minus 2g times 2 minus 2g. So this is basically 4g times g minus 1, and this is nothing but which is equal to the area P, where P is right angle regular 8g minus 4 gon. Okay, 8g minus 4 gon hyperbolic. And so, and for each I, Pi is even sided. So among every two consecutive edges, one is coming from alpha, another from beta. Okay, so therefore, number of sides of every polygon, this is 2 mi for some mi, mi is greater than or equal to 2. So alpha and beta, they are in minimal position, so no bicon is there. So therefore, number of sides will be even and at least 4. Now, if you look at alpha union beta, alpha union beta is basically a four valent graph on the surface, and complementary regions are disk. Therefore, so basically alpha union beta is one skeleton of a cell decomposition of SG, where number of 0 cells B equal to the number of intersection points of alpha beta, and valency condition gives E equal to 2I alpha comma beta, and number of faces, this is equal to the number of complementary regions, that is B. Okay. So Euler characteristic formula gives V minus E plus F equal to 2 minus 2G. So this implies that minus I alpha comma beta plus B. So this is equal to 2 minus 2G, and this implies that the intersection points between alpha and beta, this is equal to 2G minus 2 plus B. And number of complementary regions, that is greater than or equal to 1, and it is minimum when B equal to 1. And when B is equal to 1, then alpha and beta as number of intersection points as 2G plus 1. Okay, 2G minus 1. So B equal to 1 implies I alpha comma beta equal to 2G minus 1. This is the minimum number of intersection points. And in such a case, alpha and beta is called minimally intersecting. Okay, this is the minimum number of intersection points, and this is achieved when B is equal to 1. So that's why for B equal to 1, meaning the filling pairs is called minimally intersecting. Okay, so now, so E equal to 2 times intersection number between alpha and beta. So, and that is equal to E equal to 2 times 2G minus 2 plus B. Okay, and therefore the sum of number of sides EI, so this is equal to 2mi summation over I equal to 1 to B, and this is equal to 2 times, so each edge contributes 2 edges to the polygons. Okay, so this summation is equal to 2 times E, that is 4 times 2G minus 2 plus B, and this is equal to 8G minus 4 plus 4 times B minus 1. Okay. So here is the theorem. So where we have proved version of isoperimetric inequality in area. So here is the statement. Suppose Pi's are hyperbolic 2mi gons with mi greater than or equal to 2 for I equal to 1 and so on up to B, and P be a regular P be a regular n gon such that n equal to summation to m to mi plus 1 minus b times 4 is the first condition. Second condition is so area sum of area of pi over I equal to 1 to b. This is equal to area of p. Okay, then we have perimeter of p is less or equal to perimeter of pi summation over I equal to 1 to b when if p is not acute. Okay, so this is the isoperimetric inequality we have proved, and as a corollary we get Agavang conjecture holds. Greater than or equal to pi by 2. Interior angle is greater than or equal to pi by 2. Yeah. Regular means every angle is the same, right? So we have obtained this condition from here. Summation to mi is equal to ag minus 4 plus 4 times b minus 1. Okay, so number of sides of the polygon P is 8g minus 4, right? So keeping in mind, so 8g minus 4 is equal to summation to mi minus this quantity. Okay? Yeah. So one more thing. So this is an observation that number of sides is in each polygon pi. Okay, so from this equation, the number of sides in each polygon pi is less or equal to number of sides in each polygon pi. This is less or equal to 8g minus 4 because so this is even at least 4. Okay, at least 4 and less or equal to 8g minus 4. Now to answer the question on isoperimetric inequality for disconnected region, we have the following theorem. So this is the theorem for M equal to either R2 or sphere S2, and P regular n-gon, n is greater than or equal to 3, and so if C is any configuration of polygons P1 and so on up to P k such that number of sides pi this is less than or equal to n, and sum of areas of Pi. So this is equal to area of P, summation over I equal to 1 to k. Then perimeter P is less than or equal to sum of the perimeters of the polygons Pi, summation over I equal to 1 to k. So for any configuration, it is true in Euclidean and spherical geometry. The proof is very easy. So basically, for m equal to R2, so what we have is perimeter P square equal to perimeter Pi square summation over I equal to 1 to k. Okay, and for k equal to 2, perimeter of P and perimeter of P1, P2, they form the side length of a right angle Euclidean triangle. So for general k, we have this equality, and from this equality, this inequality follows. And for m equal to sphere, the strategy is idea. We prove for k equal to 2, and then by repeated application of the initial case for k equal to 2, we get the general case. Don't have much time, so okay, let me sketch the proof for sphere. So the perimeter of P, so we assume k equal to 2, and theta 1, theta 2, they are the interior angles of P1 and P2. So they are the interior angles. Then perimeter of P is equal to 2n cos inverse cos pi over n over sine theta over 2, and therefore it suffices to prove that to show. So what we show is perimeter of P is less or equal to perimeter of P1 plus perimeter of P2, and so it suffices to show that cos inverse cos pi over n over sine theta over 2 is less than or equal to cos inverse cos pi over n sine theta I over 2 summation over I equal to 1 to 2. And this inequality follows from the fact that the function, so theta, so this interior angle has the following bound. So theta lies between so this is less than pi and greater than n minus 2 over n times pi. So here equality holds. So when theta is equal to this n minus 2 over n times pi, then the polygon is degenerate. And okay, so this inequality follows from the fact that the function f of theta, so this is equal to cos inverse cos pi over n over sine theta over 2. This is strictly concave. Okay, on the closed interval n minus 2. Okay, so here let me use the parameter as x. So this is x in the interval n minus 2 over n pi comma theta. Okay, so this is strictly concave, and and so here is the interval n minus 2 over n pi, and let's say this is pi, and here you have theta, and then we have theta 1 and theta 2 in the interval n minus 2 over n and theta. Also theta 1 plus theta 2 equal to theta plus n minus 2 over n times pi. This is because of area of P is equal to area of P1 plus area of P2. So using this relation and Gauss-Bonnet theorem for spherical geometry, we have theta 1 plus theta 2 is equal to this. Okay, so and this is strictly concave, and so it implies that f of theta plus f of n minus 2 times pi over n, this is less than or equal to f of theta 1 plus f of theta 2. Okay, and this is equal to 0, and f of theta is basically the left hand side, and this is basically the right hand side. Okay, so this is the idea of the proof of isoperimetric inequality for spherical geometry for disconnected regions. Now, what about hyperbolic geometry? So in hyperbolic geometry, this theorem is not true. So this is theorem 1. Theorem 1 is not true when M is equal to hyperbolic plane. So for example, so consider, so for epsilon greater than 0, sufficiently small, consider T epsilon. This is the triangle, hyperbolic triangle with equilateral triangle with interior angle epsilon, and consider T1, T2, they are equilateral hyperbolic triangles with interior angle pi over 6 and pi over 6 plus epsilon, so that area of T epsilon is equal to area of T1 plus area of T2. Area of T epsilon equal to area of T1 plus area of T2. Now, perimeter of T epsilon tends to infinity as epsilon tends to 0, right? And perimeter of T1 this is equal to, by hyperbolic trigonometric formula, one can compute it. So this is equal to 3 times cos inverse 3 plus 2 root 3. So hyperbolic cosine formula gives this, and perimeter of T2. This is so when epsilon decreases to 0, perimeter of T2 that increases to perimeter of T1. So this is increases to perimeter of T1 as epsilon decreases to 0, and therefore, so basically perimeter of T1 plus perimeter of T2, this is bounded above by 6 times cos inverse 3 plus 2 root 3. So basically this is bounded. So perimeter T1 plus perimeter of T2, this is less or equal to 6 times cos inverse 3 plus 2 root 3, and so its value like 15 times 3 2, and this is less than 16, and for epsilon equal to 0.05 perimeter of T epsilon, this is greater than 22. So this example shows that theorem 1 is not true in hyperbolic geometry. So before I stop, let me state the theorem what we have proved. So theorem, let P be a regular and hyperbolic n-gon with interior angle theta, then there exists some capital theta belongs to 0, n minus 2 times pi over n, such that if the interior angle theta is greater than or equal to capital theta, then for any configuration P1 and so on up to Pb of polygons, hyperbolic polygons with number of sides Pi less or equal to n and area sum, area of Pi summation over I equal to 1 to b, this is equal to area of P. We have perimeter of P is less or equal to summation perimeter of Pi summation over I equal to 1 to b. And second item is if theta less than capital theta, then there is such a configuration Q1 QB, so such that side length of each QI is less or equal to n, and area sum is equal to area of the polygon P, such that perimeter P is greater than summation perimeter of Qi I equal to 1 to b. Furthermore, so this capital theta is so let us describe this capital theta. description of capital theta. Okay, so first we have the function gn defined on 0 to n minus 2 over n pi to r. So this is defined by gn of x or maybe theta. So this is equal to cos inverse cos pi over n. Okay, theta gn. Okay, so sine theta by 2. So probably I have defined before. Yeah. So this is the okay. So this is cos inverse. So this is basically, so if this is a triangular section of the polygon P, and this is the side length S, then S over 2, this is the half of the side length of the polygon P, then S over 2 is basically gn. Gn of theta is equal to this length, half of the side length. And now what is theta? Theta is basically, so now we define another function, hn, not hn, this is phi n. Phi n, this is defined on the same interval. Okay, so this is hn. So hn is, okay, hn is defined by hn theta equal to 2 gn theta over 2 plus pi over 2 minus n pi over n minus gn of theta. And so one can show that this function has unique 0. Okay, so capital theta, this is the unique 0 of small hn. Okay, and this is the description of this theta. And the proof of this theorem uses some basic calculus, so concavity, mean value theorem, etc. Okay, I have to stop now.
So can you explain in the AH conjecture?
Sorry?
In the AH conjecture, why are they interested in pairs of curves as opposed to more larger collection of curves?
Yeah, that one can study. So this is the boundary extremal case. So when you increase number of curves, so you have more chance to fill the surface. Yeah.
Yes. Okay. But can your theorem be used to say something in the situation where you have more than two curves?
Probably yes. So
Okay.
probably some restriction will be there.
Okay.
Any other question? If not, let's thank the speaker again.